Hello everyone. In this lecture, we are going to talk about Caratheodory's theorem. It is in convex geometry. So let's see what it states. It states that if a point X is in RD and it lies in the convex hull of a set P, then X can be represented as a convex combination of at most D plus points in P. So Y1, Y2, Y3, and so on till Ym, where let's say M is greater than or equal to D plus 1. And we are saying that there is some X which belongs to convex hull of this P, which can be represented as convex combination of at most, sorry, so at most D plus 1 points in P. So now there is a subset of, let's say there is a subset of P, that is P dash, consisting of D plus 1 or fewer points, such that X lies in the. Okay, so we need to prove that X belongs to convex hull of this P dash subset of P. Okay, now let's take a look at the proof. Before starting the proof, we know that if m is less than d plus 1, then it's quite trivial because for the remaining alphas, for example, I just have 5 alphas, but I have points, 10 points. So I'm just going to represent it in a convex combination such that I have 5 alphas assigned to 5 points, but for the rest of the points, the value of alpha is going to be 0 and our purpose will be solved. Now let's take a look at the case where m is greater than d plus 1. We know that x belongs to convex hull of P, and let's say that P consists of, so P consists of this points. So y1, y2, as I mentioned before, ym. Okay. So this is an equivalent statement that we can represent x as a convex combination of alpha 1, y1, alpha 2, y2 till alpha m yn, such that the sum of all the scalar multipliers, that is sum of alpha I, is equal to 1, and such that each alpha is greater than or equal to 0. Now let's take a look at m when m is greater than or equal to d plus 2. We know that these points will be affinely dependent, and since they are affinely dependent, there exists a gamma such that all the summation of all the gammas is 0. This is the property of a finely dependent set. If you're not aware of it, I would suggest you to go and take a look at it. So we have this gamma, and now we are dividing this gamma. Okay, so I said that the sum of gammas is 0. So of course there exists some which are greater than 0. So let's say this sum which are greater than 0, positive, are represented as gamma I, and the ones that are negative are represented by J. Let's define a tau such that it is minimum of alpha I upon gamma I, where gamma I is of course greater than 0. Basically, it's alpha I dash is equal to alpha I minus this tau alpha gamma I greater than equal to 0. Why is this sign important, greater than equal to 0? Because in the end, when we'll be able to represent it, when we'll finally prove it, we'll need such a scalar multiplier who is greater than equal to 0, right? As the property of convex hull. So for that, we need that it has to be greater than equal to 0. And how are we going to prove it? So let's try to analyze this function where it is alpha I minus tau of gamma I. Now tau gamma I, so I'm just going to write this tau gamma I, alpha I upon gamma I, right? So gamma and gamma gets cancelled, minus alpha I. If this alpha I is equal to this alpha I, so the minimum one is this itself, then it is going to be 0. But in all the rest cases, this alpha is going to be the minimum one because we have defined the function tau like that. So this is always going to be greater and this is going to be the less one. So this is going to be greater than equal to 0. Okay. So we have established the fact that alpha I dash is greater than equal to 0. Let's say this as equation 1. We also know that we can represent this in the form, okay, we can represent this in the form of alpha 1 y1, alpha 2 y2, and so on, dash, okay. We know that we don't need to consider this one, so because this is going to just simply going to be 0, so we consider m minus 1 summation, and our motive will of course be that we can represent this m minus 1 summation equal to x, because we need to prove that x belongs to convex hull of P dash where P dash is subset of P, right? So now we have established that for P dash, we're going to have alpha I dash, which is greater than equal to 0. We also need to prove that alpha I dash, the summation of alpha I dash is equal to 1 from I equals to 1 till n. And we also need to prove that this x is equal to some summation, convex combination, right? These are the things that we need to prove. So, yeah, let's try to analyze this sum. From equation 1, we can write that alpha 1, we can write this whole thing we can write, and I've taken similar terms on one side. Now we know that gamma 1, y1, gamma 2, y2, this sum is going to be 0 because we are finely dependent. And we know that this is equal to x. So this is the required result we already got. Now let's take a look at the property where we have to prove that this is equal to 1. The property where we have to prove that alpha I dash is equal to 1. Let's take a look how we are going to do this. Let's take a look how we'll do this. Okay, so we already have that alpha I is greater than equal to 0 and alpha I is this. So let's write alpha dash in terms of alpha I, because alpha I is what we have been given already. We know some equations related to alpha I and some values. So we'll take alpha 1 dash in terms of alphas. Okay. Uh, okay. Well, now we know that this tau is just going to be 0 because this summation is 0, are finally dependent. So we have been left with this sum equal to this sum, which implies that we have this. This is again the important result. So yeah, we proved what we wanted. We wanted to prove this. We had this and we wanted to prove this. We wanted to prove this fact, and we did. So I'll just quickly summarize that we had been given that X belongs to convex hull of P, and we wanted to prove that X belongs to also convex hull of P dash such that P dash is subset of P. For that, we needed that we already had this. We already had this fact. Yeah, we already had this fact, and we needed that there exists some alpha dash that can also be represented x. We did that too, and such that this alpha dash for all I is greater than equal to 0. We also did prove this from equation 1. And we also wanted to prove the fact that the summation of alpha dash is equal to 1. And we also did prove this fact. So yeah, that is the proof. Thank you so much for watching my lecture. Goodbye.